All right, I think we're live now, so I'll share my screen. Can you guys all see that?
Yes.
Yes.
And on my pen. So first off, just kind of general information about the exam. The exam is available in any ACC testing center. So you don't even necessarily have to go to the one that you specified in that survey that we took at the beginning of the year. You can go to any one that you want to. And they'll actually just print it out for you at the testing center, and you'll take it, and then they'll mail it back to me. So the test is available starting now and or started previously, and the deadline for taking it is this Saturday. So just make sure that you complete it by Saturday and including Saturday. Excuse me. But make sure you do check whatever testing center that you want to go to, because they all have different hours and some of them are not open on the weekends. So make sure you plan accordingly. The test itself has, I believe, 29 questions on it, and they're kind of a mixture of different types of questions. There's some multiple choice, there's some short answer, there's some problem workout kind of questions. The thing about this test and this class really is that it is a different kind of math class. It's not like any other math class you've ever taken. So the tests are not going to be like any other math test that you've ever taken. You might even be surprised by, I guess, the small amount of math on the test. There's still enough math, but there's so much more involved to statistics than just the math part. It's a lot about the concepts. So I'm going to be asking questions about the concepts and things like that. But a really good way to study for the exam, besides coming to this review session, of course, is to look at the test review that I have posted on Blackboard. So the first page of that test review is going to have terms and concepts, and you can kind of go through that and think about what those things mean and what kinds of questions I could ask about those. And then the back side has problems that are going to be similar to the types of problems that I'm going to ask on the exam. And also going through all your past quizzes is another good way to study for the exam, because quizzes should have similar questions to what you're going to see on the exam. So going into the exam, the average time to take this test is about 1.5 hours, but depending on the type of test taker that you are, it might take longer or shorter than that. So be sure to plan for yourself at least a 2-hour window to take the exam so that you have plenty of time. You can take your calculator. In fact, you should take your calculator with you to the exam. If you've never taken a test in an ACC testing center before, just know that you need to have your ACC ID with you when you go. And if you don't have one of those, you'll need to go to an ACC campus first and get your ACC ID first. You can ask for scratch paper. They'll give you scratch paper, graph paper, things like that. And you can also take in 1 page of notes, so like a cheat sheet. And so it just has to be, you can only have one, and it has to be handwritten. So everything that's on there has to be handwritten. So you can't print things out and shrink them down or photocopy the textbook or something like that. It just has to be handwritten by you on that sheet. But beyond that, you can put whatever you want on there. On the exam already, I'm going to have the formulas and the tables that you need. So usually what people put on their cheat sheet is definitions or examples, or some people recopy their notes really, really small on it, or all kinds of things. So any questions about the exam itself, like just the general things about the exam? All right, so perfect. So as we go through, feel free to speak up. I'm gonna try to make this a little bit interactive. I'm gonna ask you guys questions. And right now I have you all on mute, but if you can turn yourself back on and talk to me anytime that you want to, or I can see little images of you guys all over in the corner. So, you can make hand signals, things like that. There's also a chat window, and you can type questions into the chat, and that'll put a little flashing thing on my screen, and I'll read what you wrote in the chat and try and answer questions that way too. All right, so first off, talking about categorical versus quantitative variables. And On the exam, there's going to be a list of variables kind of like this, and you're going to decide which ones are categorical and which ones are quantitative. So a categorical variable places an individual into a group or a category. And a quantitative variable takes numerical values for which it would make sense to do things like calculate averages. So when I'm trying to decide whether or not something is categorical or quantitative, then I ask two questions. So first question I ask is it a number? And second question I ask is, would it make sense to talk about the average, fill in the blank with the variable name? So would it make sense to talk about the average and whatever it is? So if the answer to both of these questions is yes, then it's a quantitative variable. And if the answer to either of these questions is no, then it's going to be a categorical variable. So we're going to go through this list over here. And since I can see you guys all on most of you on your cameras, then if you think it's categorical, then just try to make like a C with your hand. And if you think it's quantitative, then try to make a Q with your hand. So we'll kind of go through these. So eye color. Think eye color is categorical or quantitative? Perfect, categorical. Okay, height, categorical or quantitative? Yep, quantitative. How you feel about statistics on a scale of 1 to 10? Is that categorical or quantitative? Okay, perfect, quantitative, because it's a number and it would make sense to talk about the average rating for statistics, like from our class or something. Income, is income categorical or quantitative? Yeah, perfect, quantitative. Favorite ice cream flavor? Categorical, excellent. Age? Good job. So age is one that sometimes throws people off because on some surveys, they kind of lump things together and try and turn it into a categorical variable. But if all you're given is age, then, asking those two questions, is it a number? Well, yes. And would it make sense to talk about the average age of people in our class? Yes, it would. So, so that makes it quantitative. All right, and the last one, number of times you've been to Disneyland, categorical or quantitative? Absolutely, quantitative. Okay, so once we've collected our data and we've kind of decided if we have categorical or quantitative variables, the very first thing that we always want to do with our data is graph it. The picture is worth 1,000 words. And the different graphs that we've talked about in our class so far are the ones listed here. So we have bar graphs, pie charts, histograms, stem and leaf plots, time plots, and box plots. So basically, if we have a categorical variable, then the best choice for a graph is going to be a bar chart. So this is for categorical variables. Anytime we have only categorical variables, bar graph is going to be the best option. Pie charts were mentioned in your book, and there's some scenarios when you can use a pie chart, but I don't like pie charts. They're much more difficult to read, and there's a lot more ways you can kind of distort a pie chart to make it look the way you want it to. So I would always say, why use a pie chart when you can use a bar graph? Because a bar graph is so much better. So anytime we're talking about categorical variables, choose bar graph. Then we have histogram and stem and leaf plot. And the purpose of both of these is the same. The purpose of these is to look at the distribution of a quantitative variable. So histogram or a stem and leaf plot looks at a distribution of a quantitative variable. And when we're looking at the distribution of a quantitative variable, then what we're looking for is shape, center, and spread. And the purpose of these, like I said, is the same. So really, either one of these is acceptable when we're looking for the distribution of a quantitative variable. So does it really matter which one you do? Well, most of the time, if you have a computer, then a histogram is really going to be the better option because histograms are kind of nice, pretty graphs, and Minitab does histograms fabulously. So we typically go with histograms in that situation. If you're doing a graph by hand and you just have a small data set, then I think stem and leaf plots are easier if you're doing a graph by hand. So that kind of breaks down when you would choose which one of those. Now a time plot, the purpose of a time plot is to just see how a quantity changes over time. So I'm going to see how quantity changes over time. So we're really just looking for trends or patterns in a time plot. And what we can't see is shape, center, spread. You can tell spread a little bit, but shape and center definitely, you cannot see those on a time plot. And then box plots. Box plots are great for comparing groups. So comparing groups for a quantitative variable. And you can't tell shape on a box plot, but you can look at center and spread. All right, so that's kind of a breakdown of the different graphs that we've talked about. So what do you need to know as far as the exam goes for these different graphs? Well, you need to know which graph is appropriate for a certain situation. So I'm going to give you some scenarios, and you would tell me what would be the best graph for that particular scenario. You also have to be able to interpret the graphs. So I'm going to have some of these graphs on the test, and I'm going to say, hey, you know, tell me what kind of information you can get from this graph. So you need to know what to look for on each of these different graphs. And then finally, you need to be able to construct any of these graphs. So if I gave you some data, you should be able to make any of these graphs on the exam. So we have some examples that we're going to go through here. So this first data set that we're going to look at, this is the top 100 NBA players in 2013. So I couldn't fit them all on this slide, but this kind of gives you a general idea of what this looked like. So the full data set that I got the graphs from had all 100 on it. But it had the player rank, it had the player name, their position, their height, their weight, what team they were on, and whether or not they were on a playoff team. All right, so suppose that you wanted to examine the distribution of NBA player weights or NBA player heights. What do you think would be the best graph to do this? So it's tricky, but see if you can make the letter with your hand. So A, histogram, B, stem and leaf plot, C, bar chart, D, time plot, or E, box plot. I don't know how you make an E. Make a sideways thing with like this for an E. So A, you can kind of do B, C. You can almost make it with your hand. All right, okay, I see some A's out there, and histogram would definitely be a good choice for this. So histogram, purpose of a histogram is to look at the distribution of a quantitative variable, and weight and height are both quantitative variables, so histogram would be a good choice. Stem and leaf plot would also be an acceptable choice for this one as well. So here is a histogram of the weights of those NBA players, and on a histogram, we're looking for three things. We're looking for shape, center, and spread. So shape is what's the overall pattern. And what we're really kind of looking for is it symmetric? Is it skewed right? Is it skewed left? Or something else? So looking at the histogram of weight, what shape would you say that it has? And again, you can see if you can make the shape of the letters with your hands. All right, okay, I see a couple of things there. So this one is pretty much symmetric. So if we kind of just generally look at the pattern there, it does look fairly symmetric. So we have a symmetric distribution, and when I'm looking for center, it's pretty easy on a symmetric distribution because it's going to be right in the middle there. So I'd say the center is somewhere around 230 pounds, and it looks like it spreads all the way from about 170-ish up to like 290 or maybe even 295 up there. So those are the three things that we look for in a histogram: shape, center, spread. So here's a histogram of the heights of those basketball players. And what shape would you say that the heights have? Symmetric, skewed right, skewed left, or other? All right. So I would say that this one is more skewed to the left. We do have this kind of weird blip thing that hangs out here, but in general, this one is pretty skewed to the left. Now, when you're looking at skewness, we identify the skewness by the tail. So the tail is kind of where the outliers are. It's where the less data is. So our tail in this case is on the left, so that would make this one skewed left. And if you have a hard time identifying skewed left, skewed right, then I recommend going and watching the video in the week 1 folder where I show you my memory trick for histograms, because it's kind of a silly memory trick, but totally works wonders. So check that out if you have it. So looking at this one shape, we've got that one skewed left. So when we're looking for center when it's skewed, we do have to take into account that we have a bunch of data all over here and less data over there. So if we were trying to find a place where we could draw like a vertical line where it would cut the area of the histogram exactly in half, then maybe that would be, I don't know, maybe it would be somewhere around here, maybe around 80, maybe even a little bit higher, like 81 or so, or where this would kind of balance on a point. That's how we kind of identify where center is. So I would say like 80, 81 for our center here, and then it looks like it ranges from about 70 inches up to about 86 or 87 inches. All right, suppose you wanted to examine the distribution of NBA player positions. What would be the best graph to look at for that, for player position? Any guesses? Yeah, awesome. Okay, so bar chart. So player position is categorical, and anytime we're just looking at a categorical variable, then bar chart is the best answer. So here's a bar chart of position, and the question here, I mean, I have this little thing up in the corner that says symmetric, skewed left, skewed right. This is kind of a trick question though, because is there such a thing as shape on a bar chart? And the answer is no, there isn't, because in a categorical bar chart, the order of the bars is a little bit arbitrary. So I could change around the order of the bars. I mean, I think right now they're in alphabetical order, center, forward, guard, but there's no magic to that order. We could rearrange these bars into be any order we want to, and it doesn't change the interpretation of the graph. So we do not describe a bar chart by looking at shape. So what do we look for on a bar chart? Well, on a bar chart, we're going to look at the categories. So we can see that in this case, there was 3 categories. There was center, forward, and guard. So those are the 3 different positions. And we can look at frequencies. And we can kind of compare frequencies. So looking at this, I can say, okay, well, of those top 100 NBA players, the position with the most players was guard, and the position with the least number of players was center, and then forward was somewhere in the middle. So that's all we can get from a categorical bar chart. So just keep in mind that we look at different things on a categorical bar chart versus a histogram. And don't try to describe a bar chart with all the histogram terms or you'll get it wrong. So don't talk about shape, don't talk about center, don't talk about spread on a bar chart, because those things only apply to quantitative variables. And when we're looking at histograms or stem and leaf plots. All right, so here's another data set. This data came from one of my students who went to run the Denver Marathon, and she went around and asked people, fellow marathon runners, how many weeks they had trained for that marathon, how many marathons they had run previously, and then she wrote down their names, so at the end she could go back in and figure out what their time was for the marathon. And she also wrote down their gender. So suppose you wanted to examine the distribution of marathon times. What would be the best graph to do this? So looking at marathon times. All right, so I see some votes for B, stem and leaf plot, and that would be a great choice. We could also do histogram in this place too. So anytime we're looking at distribution for quantitative variable, then histogram or stem and leaf plot are going to be good choices. So here's a histogram of the time that it took to complete. This is all the runners together from the sample. And what shape would you say this one has? Yeah, I would say this one is pretty, roughly symmetric. Looks pretty good. Suppose you wanted to examine the distribution of number of marathons completed. What would be the best graph to do that? Yeah, same thing. I know this is feeling a little bit repetitive, right? But we have a lot of quantitative variables are some of our favorites. So we have, whoops, I don't want to do that. Hang on one second. Go back to my mouse. Okay, so histogram or stem and leaf plot would also work here. Now looking at this histogram, what shape would you say that this one has? So looking at this one, we have a big column over there, and then we have some huge outliers way out here where if you look back at the data set, somebody had run 69 marathons previous to this particular Denver Marathon, which completely blows my mind because I'm still working on getting the 1 marathon off my bucket list. I haven't been able to do it yet. So 69 marathons is totally amazing to me. Or even this person who ran 50, like that's incredible. So this one, because the outliers are on the right, then this one is going to be right skewed. So this one's a skewed right distribution. All right, suppose you wanted to compare marathon times for men and women. What would be the best graph to do this? All right, I think I see an E out there. And box plots, and yes, that is the best choice, I think. I think box plots would be a great choice. You can also do histograms or back-to-back stem and leaf plots, but I think box plots are the easiest to really see those differences. So here's some box plots side by side for male and female, and on a box plot you cannot tell shape, but you can look at center and spread. And you can compare centers and spreads. So looking at the centers of these, and remember that center line on a box plot represents the median, which we'll talk about in a minute. But you can see right off the bat that the females took a little bit longer to run the marathon on average than the males. Males were a little bit faster. Looking at kind of the overall spread here, they had very similar spreads. If kind of just looking at how spread out everything was, the boxes themselves weren't too much different. The male box was slightly larger. But so I would say that the females took longer, so higher mean, but their spread or variation was about the same. So and just for kind of comparison's sake, here are side-by-side histograms of the same data. So, and I had to do it on the same scale. So if you kind of look back and forth, you can still kind of get that females took a little bit longer. But in my opinion, like, I love the just instant visual of the box plot where it's like, oh yeah, clearly, females took a little bit longer to run the race than males. Whereas I feel like it takes a little bit more work to figure that out from looking at side-by-side histograms. Or I guess back-to-back stem and leaf plots, you can tell a little bit, but you can't get Minitab to do a back-to-back stem and leaf plot for you. So I prefer box plots. Okay, here's another data set. This is data that I collected several years ago about Taco Bell bean burritos without onions. That was my kid's favorite food back in the day. And so I wanted to find out if I thought maybe I was getting shortchanged on the amount of beans in my bean burritos. So I created this experiment or observational study really, where I went around to 5 different Taco Bells. Each one I went to 6 different times, and I ordered the bean burrito, and I secretly weighed it, and these were their burrito weights. And yes, I really am that psycho statistics person that does these kind of things. So suppose you want to see if there's any trends or patterns in the burrito weights, because these burritos were collected over time. What would be a good graph to look for trends or patterns in burrito weights? Yeah, time plot. So if we're looking for trends or patterns, then time plot is going to be the best choice. So here was a time plot of weight, and I'm looking to see if there's any trends or patterns, and there really isn't for the burrito weights, which I didn't expect there to be any trends or patterns in the burrito weights, but it's good to look and make sure that there's not any trends or patterns there. So what do I mean by a trend or pattern? Well, some typical things that we might see, like if you remember in your homework, we looked at that pup seal data, and in that one, the points had a very clear downward trend where you could see that over time the pup seals were getting less and less. So that would be an example of a pattern that you'd be seeing over time. If you look at some data, you might see kind of a cyclical pattern. So like if I look at some of my, say my like electrical bill, okay, or my gas bill, well, those tend to fluctuate seasonally because I use more heating or more air conditioner with the temperature outside. So you might see some kind of cyclical pattern. Or you might see like an increasing pattern, you know, maybe something's going up, like, I don't know, prices of college tuition or something might be like increasing over time. So, so all you're looking for on a time plot is trends or patterns over time. So taken together here, so here's a histogram of the weights and also a time series plot of the weights, a time plot. So what are we looking for on the histogram? Well, we're looking for shape, center, spread, and then on the time plot, we're looking for trends or patterns. So in this case, the shape of these weights was mostly symmetric. We did have a couple possible outliers over there, so I'm going to say mostly symmetric. The center is going to be right around 200, maybe slightly more than 200. And the spread looks like it went from about 175 to 240. These are grams. I measured these in grams. So there was quite a big range of weights of those burritos. And in case you're interested, the amount that they're supposed to weigh, if you look on the Taco Bell website, is 191 grams. So actually on average, they all mostly weighed more than what they were supposed to weigh. Okay, and we already talked about the trends or patterns. There really didn't seem to be any trends or patterns going on there, so just random. All right, so once we've graphed the data, then our next step in our data analysis is going to be to calculate numerical summaries. And we talked about numerical summaries for center and also for spread. So the two measures of center that we talked about were the mean and the median. So the mean is just the average, the arithmetic average. And we calculate the mean. Well, first of all, we call the mean of a data set X bar. And we calculate it by adding up all the observations and dividing by the total number of observations. And then the median is just going to be the middle value of the data set. So here's data here. This is the data for the female marathon runners that we looked at earlier. So first thing let's look at is the median. So there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's a total of, I'll write that up here, n equals 15. 15 observations for the females. So to find the location of the median, we can use this little formula. Just take n plus 1 over 2. So in this case, that would be 15 plus 1 over 2, 16 over 2, which would be 8. So that means that I can count over 8 observations, 1, 2, 3, 4, 5, 6, 7, 8, and that value would be my median. Now, what happens if I have an even number of observations? If I have an even number of observations, then when I get to the middle, there's 2 values, not just 1. So I would take the average of the middle 2 values to come up with my median. So once I've ordered them from smallest to largest, I'm just working my way in, and the middle number is the median. For the mean, x bar, we're going to add them up and divide by the total. So I'm going to get out my calculator here, and feel free to get out your calculators. And we're going to add up all those numbers. So we have the zeros, they're easy to add. Then I'm going to have 1 plus another 1 plus 2 plus 2 plus 4 plus 7 plus 8 plus 10 plus 69. So when I added them all up, if I did it right, maybe I'll do it one more time just to be sure. Then I got 104. And I would divide that by 15, which was my sample size. And that gives me 6.9333 as my mean. So in this case, my median was 1 and my mean was 6.93. So those are 2 pretty different numbers here for center. So how do I decide which one I want to use? The median is resistant, meaning that it's resistant to the effect of outliers. And you notice that that person who ran the 69 marathons, they were in this group. And so they are really going to affect the mean over here. It's going to make it look like people are running marathons like crazy if a typical value is 6.93 for the mean. Whereas the median was not really affected by that 69 very much, almost not at all. So when we have a skewed distribution or we have really big outliers, then we're usually going to choose the median to represent the center of the data. And if we have roughly symmetric data, then we're typically going to use the mean to represent the center of the data. So here's a graph again, and this is a graph of all of them, not just the women. And we just talked about this. So which one's going to be a better measure of center? In this case, the median is going to be a better measure of center. And for number of marathons completed, which will be greater, the mean or the median, and we saw this when we calculated it, but the mean was higher. So the mean is always pulled towards the tail. So in a right skewed distribution, the mean will be to the right of the median. And in a left skewed distribution, the outliers will be on the other side and the mean will be lower than the median. So there was like a homework question. I'm trying to remember if it was a homework or a quiz question. I think it might have been a quiz question. No, it was a homework. Anyway, where it asked you, it gave you 2 numbers and you had to decide which one was the mean and which one was the median. And you had to base it off of the skewedness and which one would be higher based on how skewed it was. So here's, the median and the mean, and you can see how different they are because the mean's being pulled towards the outliers. So here's another example. So this one is, the other one, the marathons were skewed to the right. This one is skewed to the left. So which one will be greater, the mean, the median, or do you think they'll be the same? What do you guys think? Which one's going to be higher, the mean or the median? We got mixed results on this one. So the one that's going to be bigger is the median. So the median's going to kind of stay right in the middle, whereas the mean is going to be pulled towards these outliers down here. So the mean's going to be a little bit lower. So here I calculated them. You can see the median is 87, and the mean being pulled towards those low outliers is going to be 85. So you'll notice when I report how the test did on exams, I typically give the median because exam scores are, this was from an actual exam, but exam scores are typically skewed to the left. Okay, so we talked about measures of center. Now let's talk about measures of spread or variation. The two measures that we have are the standard deviation and the 5-number summary. So the standard deviation is the average distance each point is from the mean. So the larger the standard deviation, the more spread out the points. So looking at my pictures over here, you can see that B would have a larger standard deviation because those points are more spread out. And A would have a smaller standard deviation because those points are closer in centered around the mean. And then the 5-number summary has these 5 numbers in it: the minimum, the first quartile, the median, the third quartile, and the maximum. So I don't think I have an example on this presentation of how to calculate standard deviation, but I will tell you that there is a really small itty-bitty data set on the exam where you will have to calculate standard deviation using the formula. So the formula for standard deviation is S is equal to square root of the sum of X minus X bar squared over N minus 1. So there was an example of how to do this in the chapter notes for chapter 2. So I recommend going back to look at that. I like the kind of the column method of doing it for calculating standard deviation, but take a little look at how you would do that by hand before you go take the exam, because there is a question where I'm going to ask you to do that. This is the only exam where I'm going to ask you to calculate standard deviation by hand. After this, you'll always be given standard deviation, or you can have your calculator find it. Because I know in real life, like everything finds standard deviation, like your phone can calculate standard deviation. I think it's a good practice to go through the motion of calculating it a couple times just to help you understand what standard deviation is. So that's why I make you do it on the first test. So let's talk about the 5-number summary for this data here. So first of all, start with the easy ones. Minimum, that's just the smallest number in the data set. So that'll be 0. Maximum, that's the largest number in the data set. So this one will be 69. And the median, we already found that. 1, 2, 3, 4, 5, 6, 7, 8. It was this one here. Here's the median. So our median was 1. So now we just have to look at the quartiles. And quartiles do what they kind of sound like. Quartile sounds like quarter, and the quartiles divide the data into 4 equal quarters with the same number of observations in each quarter of the data set. And we finding the quartiles is kind of like sharing a candy bar with you and your 3 closest friends. So if you had a candy bar, and we're going to make this one a Milky Way Midnight because that one's my favorite kind, and you're going to divide this between you and your 3 friends, then the way that most people would do it is they would cut it in half, and then they would cut each half in half, and then you'd end up with 4 equal parts. And that's basically what we're doing here with our data. So when we cut the data in half, that's what we're doing when we find the median. So I'm cutting the data in half right there at the median. Then I am going to find the median of the lower half of the data. That's going to be my Q1. And I'll find the median of the upper half of the data, and that's going to be my Q3. So looking at the lower part of the data here, once I cut the data in half, and if I have an odd number of observations in my original data set, then the median itself doesn't go with either side. If I have an even number, then you would separate out all the observations. So if it was an even number, then all the observations would go to either one side or the other. But if you have a leftover one here, then it's just left out. It doesn't go on either side. So since I had odd, I'm just going to leave that one out. So now I'm looking at the lower half of my data here at the middle number. There are 7 numbers there. So looking at the middle one there, then Q1 then would just be 0. And same idea with the upper half of my data. I'm looking for the middle value there, which in this case would be 7. So my Q1 would be 0 and my Q3 is 7. And it's okay that the minimum and the Q1 are the same value. That just tells me that basically the bottom 25% of the data, that bottom quarter of the data is all the same number. It's all 0. All right, so a box plot is just a graphical look at the 5-number summary. So if I wanted to draw a box plot of this data here, then, and you can do box plots horizontally or vertically. I do mine vertically. That's how Minitab does them too. Then basically I just need an axis here, my y-axis, that's going to span the range of the data. So go all the way from 0 up to at least 69. So I'm just going to make some equally spaced tick marks over here. Hopefully I can fit this all in. So I'm going to start with 0. Maybe I think I'll count by 10. So 10, 20, 30, 40, 50, 60, 70. Okay, I did not do the best job with this, but hopefully you'll get the idea of it here. So 0, 10, 20, maybe I should erase it and start again. Okay, I'm going to do that. Sorry, that was an ugly one. I want to spread it out just a little bit more so it's not quite so tiny. It's getting a little bit. So let's see, let's say 0, 10, 20, 30, 40, 50, 60, 70. So when you're making this is the most important part, is just setting up your axis correctly so that you have evenly spaced tick marks over here. The biggest mistakes that I see for people drawing box plots are people who draw a box with some lines coming out of it and then just write labels on it, and then it doesn't actually correspond to an axis or anything. Okay, so once I have my axis set here with my equally spaced tick marks, then I can start plotting the values for my 5-number summary. So for my minimum at 0, we're going to have a dot. For Q1, the median, and Q3, all of those get lines. So I've got a line at 0. I'm going to get a line at 7, and I'm going to get a line at 1. Sorry, I skipped 1. Okay, so Q1 was 0, Q2, or the median, in other words, is 1, and then Q3 was 7. So all those get lines, and those lines connect to form my box. And then the maximum also gets a dot, and that dot connects to the box. And if this was Minitab, Minitab usually just puts like a star way up there and doesn't connect everything if the outlier is like way out there like this one is. In fact, this is tough to draw on a computer screen. Okay, so this also would show us how really skewed this distribution is, or how high out there that outlier is. This would be an example of a box plot for this data here. All right, so once we've graphed the data and we've described it numerically, the next step is to model the data. And the type of model that we use to model data is called a density curve. And there's only 2 requirements for a curve to be a density curve, or in other words, to be used to model actual data. The first requirement is that all the area is on or above the horizontal axis. So all area on or above the x-axis. And if you think about the fact that what we're doing here is we're really looking at a histogram and we're kind of smoothing it out, then this requirement makes sense, because on a histogram, the y-axis is frequency. So if we're modeling real data, we couldn't have a frequency that is negative, so we would have to keep all of our area above the or on the x-axis. And the second requirement is that the area under the curve adds up to 1. So area under curve adds to 1. And that's because, again, we're using this to model real data. So the 1 actually represents like 100%. So the curve is going to represent everybody, and then we're going to look at areas under the curve to represent different parts of our population or distribution. So there's lots of different curves that can be density curves. We could have a curve that looks skewed. We could have a curve that actually looks like a rectangle and doesn't seem very curvy at all. We can have a curve that looks like a bell curve. There's lots of options, lots and lots of options. There are some curves that show up in real life more often than others, so that shape shows up, making them more useful than other shapes. So we do tend to talk about one particular family of density curves, but just know that there's lots of different density curves out there. When we're talking about density curves, we give the mean and standard deviation of a density curve special names so that we can distinguish those from the mean and standard deviation that we calculate from our data. So mu is the mean of a density curve. And sigma is the standard deviation of a density curve. Okay, so that's to distinguish them from X bar and S, which are the mean and standard deviation when we actually calculate those from our set of data. All right, and you know, we said that there's one family of density curves that are particularly useful because that shape shows up a lot, and that shape is the normal distribution. So normal distributions are the lovely symmetric bell-shaped distributions. And one of the cool things about normal distributions is that if we know something's normally distributed and we know its mean and standard deviation, then using this rule, the 68, 95, 99.7 rule, we can kind of figure out where all the observations in a normal distribution lie. So the 68, 95, 99.7 rule says that approximately 68% of the observations are going to be within one standard deviation of the mean. 95% are going to be within 2 standard deviations of the mean, and 99.7% are going to be within 3 standard deviations of the mean. So, oh, I thought I put a picture. Oh, I did put a picture. Okay. So here's kind of a picture of what that looks like. And I know I posted in the announcements section kind of a similar curve that looks similar to this, where everything's kind of broken down. So on the exam, you're not going to have any of these pictures. So if you like these pictures and this way of using the rule, then make sure you put these in your cheat sheet. But sometimes breaking it down this way is helpful. If you know exactly how much is in each of these little pieces, then it can help you answer the question a little bit easier. So here it says we have a normal distribution with a mean of 25 and a standard deviation of 6.5. So just making a little sketch of that here. Here's my normal distribution. And I know because it's symmetric, then right down the center is going to be my mean, which was 25. And standard deviation is 6.5. So I'm just going to add the value of one standard deviation going each direction here. So if I take 25 plus 6.5, then I get 31.5. That was let me make sure I'm getting the right one. Yeah, 6.5. Okay, then I have 31.5 plus another 6.5 gives me 38. Plus another 6.5 gives me 44.5. And then going the other way, I'm going to have 25 minus 6.5, which is 18.5. Minus another 6.5 gives me 12, and minus another 6.5 is 5.5. Okay, so knowing that it's normally distributed, knowing the mean and the standard deviation, I can get a picture of what this normal distribution looks like. Here's what it looks like. So the first question says, what percent of students score between 5.5 and 44.5? So 5.5 is over here. It's 3 standard deviations away from the mean. 44.5 is over here, also 3 standard deviations from the mean. And according to my rule, within 3 standard deviations, I'm going to find 99.7% of the data. So the answer to what percent of students score between 5.5 and 44.5, well, that's going to be 99.7% of the data. Next question says, what percent of students score more than 31.5? So 31.5 is right here. I'm looking at more than 31.5. So that's everything to the right of 31.5. That was kind of an ugly 31.5. Fix that. There. So this one's a little bit trickier of a question to answer using the rule. So I start by thinking, okay, what do I know about 31.5? Well, I know that it is 1 standard deviation away from the mean. And I know that within 1 standard deviation, so in this case, between 18.5 and 31.5 is 68% of the data. Well, if there's 68% between 18.5 and 31.5, then that leaves 100 minus 68, which is 32. 32% of the data to be left over here and over here, kind of in these two, really it would cut off there, I guess, in these two tails. And these two tails are symmetric. They're mirror images of each other. So that means that in this one over here, I'd have 32 over 2, which is 16% here. So that's the answer to my question. What proportion are more than 31.5? Well, 16%. So doing these problems, it's kind of just like a puzzle where you're just trying to break down what part of the curve that we're talking about. So let me show you that same problem using this curve here where everything's been broken down even more than just what the rule said. We've got each individual part here. So that 31.5 was right here, 1 standard deviation away. And if I wanted to use this picture, then all I'd have to do is add up all the pieces that are more than 31.5. So I'd have 13.5 plus 2.35 plus 0.15, and that would give me 16. So you get the answer the same way, but some people like this method a little bit better than thinking about it the other way. So the next one, what percent of students score less than 12? Okay, looking at my picture here, I can see that 12 is 2 standard deviations away from 25 on the low end, and I'm looking at less than 12. So again, if I'm looking at that on my picture over here, I'm 2 standard deviations away, looking at less than. So I would add up everything less than that. So I'm going to have 0.15 plus 2.35, which is 2.5. So there is a question on the test that specifically says use the 68, 95, 99.7 rule to answer it, and you should not use a z-score to answer that question because it says to use the rule. So you need to think about it, either this way or if you wanted to write one of these images down on your notes. If you just Google 68, 95, 99.7 rule and look at images, then several of these kind of images will come up. So if you want to put that on your cheat sheet and do it that way, you can. But if you use a z-score, you're going to get a slightly different answer, and you'll get it wrong because if the question specifically instructs you to use the rule, then I'm expecting you to use the rule. But the rule is only good for distances that are exactly 1, 2, or 3 standard deviations from the mean. So if we have something that's different from that, then we're going to have to use the z-score and table A in order to find the area that we're looking for there. So here's some examples where we actually use the z-score to help us find areas under the normal curve. So this one says, the professor knows from past experience that the time for students to complete a quiz is normally distributed with a mean of 21 minutes and a standard deviation of 3 minutes. If he allows 25 minutes for the quiz, what percent of the students will not finish the quiz? So this is a normal distribution kind of problem because it tells us these are normally distributed. It tells us what the mean and the standard deviation are. So the first thing I do for these kind of problems is draw a picture. So I know it's a normal distribution, so I sketch that out here. And I put right in the center, I'm going to put my mean, which was 21 minutes. And then I know that pretty much the whole normal curve fits in a 3 standard deviation distance from the mean. I know that because of that 68, 95, 99.7 rule. So I put 3 equally spaced tick marks on either side to represent the 3 standard deviations. And I can put the values for those in as well. So I take the 21 plus the 3 gives me 24, plus another 3 gives me 27, plus another 3 gives me 30. Going the other direction, I'm going to subtract a value of the standard deviation. So I'd have 21 minus 3, which is 18, minus another 3, which is 15, minus another 3, which is 12. So all I've done is just add and subtract standard deviation values going either direction until I had 3 on each side. So it says he's going to allow 25 minutes for the quiz. So 25 is about right here on my picture. And we want to know what % of students will not finish the quiz. So if they're not going to finish the quiz, that means it would take them longer than 25 minutes to complete the quiz. So I'm going to shade in everything that is longer, or in other words, greater than 25. And that area right there is the answer to my question. So I just had to find that area. Now, unless you are a calculus genius, then the best way to find the area under this curve is going to be to use table A. So in order to use table A, then we standardize and then we go to the table. So to standardize, we use our z-score formula. So z is equal to x minus mu divided by sigma. So the x that we're looking for, it comes in the question. So we're looking at 25 minutes for our x. And then the mu and the sigma are also going to be given to us in the problem. So 25 minus the mu, which was 21, and divided by sigma, which was 3. So 25 minus 21 divided by 3 gives me 1.33. So the table only uses 2 decimal places, so you can round to 2 decimal places for your z-score. So what does this z-score tell us exactly? Well, it's a measure of how many standard deviations your point is from the mean. So a z-score of 1.33 says that finishing the test in 25 minutes would be 1.33 standard deviations above the mean, or longer than average in this case. All right, once I have my z-score, then I go to table A, and I'm going to look up that 1.33. So to use table A, and I'll write my z-score over here real quick. So my table, my z-score was 1.33. So in the table, we look up the ones and tenths place over here in the far left column. And then the hundredths place is what we look for along the top over here. So I start with the 1.3 for my z-score, and then my hundredths place had a 3 in it. So I look for the 0.3 here column, and where those two intersect is the value that I'm looking for. So I have 1.33, and the table tells me 0.9082. Okay, 0.9082. So table A says 0.9082. Now the table always gives you, maybe I'll go back to the table, gives you percentiles. So all these numbers here in the middle of the table, they are percentiles. Well, what's a percentile? A percentile tells you what percent of the people were below you. So this says that if your z-score is 1.33, then 90.82% of the people were below you. So it basically always gives you the area to the left. But looking at my picture here, I didn't want to know the area to the left. I wanted to know the greater than, or the area to the right. Well, no problem. Okay, what the table told me was over here, 0.9082, but I know that the whole curve is 1 because it's a density curve, so the whole curve has to add up to 1. So if I want to find this area, the greater than area, I just take 1 minus 0.9082, which gives me 0.0918. And that is the answer that I'm looking for. So what percent of students will not finish the quiz? 0.0918, or you can change it to a percentage, 9.18%. And this is one reason why I always draw a picture, because if you look at my picture over here, you can see that that shaded area should be a percentage that's smallish, you know, definitely less than 50%. So if we look at the number I got from the table, that's a big-ish number. So I'd be like, okay, that's not the right answer. And realize that I'd need to subtract from 1. All right, next question. Suppose that he wants to allow sufficient time so that 95% of students will complete the quiz in the allotted time. How much time should he allow for the quiz? So this one is different from the other one. The other one gave us a time, an X value, and our answer was a percentage. This time we're given a percentage, and our answer is going to be an X value. So this one is a backwards normal kind of problem. So I still start by drawing my picture. I'll get it back up there again. So 21 was the mean, 3 was my standard deviation, so just adding 3 every time, then subtracting 3 every time, same way I did before. Just making my picture again. Okay, but this time it says he wants 95% of students to complete the quiz in the allotted time, meaning that 95% will be that much time or less. So I don't know exactly where that's going to be, so I'm just going to put kind of a dotted line here, because that's what I'm trying to find out. But what I do know is that the area less than that is going to be 95%. Okay, or in other words, the 95th percentile is what I'm looking for. So because it's a backwards normal problem, I start in the table, I look at the percentile, use the percentile to find the z-score, and then I use the z-score to find the x value. So I'm doing all that stuff in reverse. So I'm going to start by look in table A for the percentile closest to 0.95. So look in table A for percentile close to 0.95. So there's two halves, two sides to the table. So I'm looking in here. The percentiles are all the part in the middle. I'm looking for the closest one to 0.95. And you can see that there's these two right here. One's 0.9495, one's 0.9505. They're both equally close to 0.95, so you could go with either one. So I'm going to choose this one, 0.9505. Once you find the percentile, now you need to find the z-score. So you do that just by looking up the row and up the column here. And I can see that the z-score that corresponds to the 95th percentile is 1.65, or you would have gotten 1.64 if you chose the other one. Either one would be fine. So I get a z of 1.65. All right, so I'm going to write that down here. So I get z equals 1.65. Now, recall our z-score formula is x minus mu divided by sigma. So now I just found out z. I know mu and sigma because they were given to me in the problem. So I can plug in everything I know and solve for x. So I'm going to have x minus 21 divided by 3. So now I've got it all set up and I just need to solve for x. So I'm going to take 1.65, multiply both sides by 3. So if I do that, then I end up with 4.95 equal to x minus 21. Then I'm going to add 21 to both sides. And I end up with x equal to 25.95. And that's my answer. So if I want to or if the professor wants to allow enough time so that 95% of the class finishes the quiz, then he needs to allow 25.95 minutes, or essentially 26 minutes, in order to complete the exam. All right, I think, yeah, that's all that I have. We went slightly over our hour by about 5 minutes. Does anybody have any questions or anything that they want to ask? And I'll just go ahead and hang out for a few minutes. If anybody has questions, you can feel free to hang out and ask. And let's see.
Quick question.